This is the first webinar of a series that I'm planning to present over the next several months or so. And today the presentation, the focus is to give an overview of MIL Standard 461G and also to talk about some of the platforms that we do testing for equipment getting installed on certain military platforms, to give an example of some of the upcoming platforms, as well as to talk about from a contractor point of view how you would prepare to plan for conducting MIL Standard 461G testing. So this is a quick outline of what I'm going to attempt to cover. I'll go over a quick revision history of MIL Standard 461, discuss some of the latest military platform examples, and then I will provide an overview of MIL Standard 461. And then I'm going to specifically talk about some of the changes that were implemented in the most recent version, which is version G of MIL Standard 461 compared to the previous version. After that, I'll discuss how to plan for testing, and then I'll also include some of MET's capabilities, related capabilities. So MIL Standard 461 version A was released in 1968, and approximately every 6 to 10 years, somewhere in that time frame, since then, there's been a new version that's released. So there's a committee for MIL Standard 461 that periodically meets, and they try to make improvements to the standard and keep updated with the latest technology and everything that's been learned through everyone's experience. So the latest version, MIL Standard 461G, was released at the end of 2015. Some of the key differences between versions of the standards are listed on this slide. Versions A through D, in those versions, they actually had two separate documents, MIL Standard 461, which contains the test requirement, and then MIL Standard 462, which contains the test procedures. And after version D and E through G, they combined the requirements and the procedures into a single document, and they maintained the 461 number and dropped the 462 document. Another key difference is in versions after versions A through C, there was the most major rewrite of the standard, most major revision, and they even changed the test method numbering system from a 4-digit to a 5-digit numbering system. And it's important to note that even when comparing between the older versions A through C to D through G, example CE02 and CE102, when you see similar numbers, they don't necessarily represent the same test method. Some test methods were completely dropped. New test methods came into play. So it's the most major changes at that point. And then after version D, they also, as I mentioned, they dropped 462 altogether and combined everything into one document. Also to note, in versions A through C, those versions of the standard, they didn't include test system calibration procedures or requirements. Starting with version D and on, they introduced a test system calibration for each test method, which is very valuable, and it was, I feel, one of the great enhancements of the standard. And the test system calibration requires that every time a test method is performed, first there's a known signal that's measured to validate the integrity of the test system, which gives a strong evidence that everything in the test system is working properly, and it gives more confidence in the test data. In versions D through G, like I said, they added the calibrations, and they provide calibration setup diagrams as well as step-by-step procedures on how to do those calibrations. The calibrations also in addition to ensuring that none of the test equipment has been damaged or is malfunctioning, it checks the test software and correction factors, and gives a good integrity that the entire test system is working well. Another change that took place is in versions A through D, after the initial release of versions, the military would frequently release notices, and the notice would offer some minor revision to the standard, but not to the point of releasing a new version. And it was a little cumbersome because the notices would only contain a few pages that contain the revision. So in order to use electronic documents, which are mostly used today, it would be difficult. You would have to open multiple documents and keep in mind all the notices. So that hasn't happened. There may have been a few notices that came out since then, but they don't majorly change the content of the standard with those notices. So the next series of slides, just trying to give some examples of some upcoming new platforms that are planned to be released by the different military branches. And the reason that I'd like to include this is when we're testing for MIL Standard 461 or some of the other standards we test for, we're normally testing sub-assemblies, not the full platforms and not discrete components, but in between that level, so sub-assemblies that are going to be installed on platforms. And it's important to recognize some of the platforms. One important note that has to do with the versions of standards when we start talking about platforms is MIL Standard 461 testing is normally done to the version of the standard that was in place at the time the platform was initially designed. So even though some platforms that are in use are very old, they still periodically update the sub-assemblies within the platform. And so even though currently version G is the current version of the standard, as a test lab we frequently test to any of the older versions of the standard that were in play at the time the platform was designed. In fact, to date, even though version G of 461 was released at the end of 2015, so far MetLabs has only conducted a few test programs to version G for that reason that I explained, because most of the platforms that equipment are being installed on were designed prior to that time. So many of the test programs we've done in the past few years are still to version F, and there's also test programs we've done to all of the older versions. So the first example vehicle, the platform that I show is an amphibious combat vehicle, and ACV for short, and this is something that was initiated by the Marine Corps Systems Command and is planned to replace the expeditionary fighting vehicle. Some of the design requirements that have been implemented are that this platform needs to be able to handle direct and indirect fire countermeasures. It needs to implement those type of technologies and functions, as well as landmine countermeasures. It also needs to have visible and thermal signature detection equipment and capability, and it has to have the capability of accepting modular protection when desired. One of the top requirements of the design was the speed on water, increasing the speed on water. Although it is designed as a fully amphibious vehicle, so it needs to have quite high capabilities on land as well. Looks like I accidentally relisted some of the capabilities here, but beyond that, the capability to transition from water to ground with no pause, capability to maneuver with up to the performance level with M1A1 Abrams tanks, and it has to be designed to have the capability to destroy similar combat vehicles. Has to be able to have weapon system that operates sufficiently for a standoff distance, and it needs to be able to support direct fire support for dismounted infantry. Another upcoming platform, just as an example of something for the aircraft, is the Boeing TX trainer. This is a aircraft that's recently designed, and Boeing is proposing this aircraft to the U.S. Air Force as a trainer aircraft. So the aircraft will have a single G404 engine, twin tails, stadium seating, and an advanced cockpit with embedded training capabilities, which are able to simulate various current and future fighters. And then the last example that I give of an upcoming platform is the Navy USS Gerald R. Ford aircraft carrier. So this aircraft carrier and others like it are scheduled to replace the Nimitz-class carriers. And the Gerald Ford, at the time of the information at the sources that I took some of this information, was currently at the Newport News shipbuilding yard or shipbuilding company in Virginia. And some of the capabilities of the design is it's designed to house 2,600 sailors, but which is actually a lower number compared to the previous carriers, but that's because the design requires fewer sailors to fully operate it. And then an air wing designed to house 4,600 crew members. Some of the new technology that's designed for this aircraft carrier, the power generation system and the aircraft landing system and processes, as well as the weapons elevators. So that just gives an example of some of the platforms that drive the need for the subsystems that we test at Met Labs. Most of the subsystems we test are designated for a particular platform, although we do get projects where we're testing subassemblies that might be suitable for a variety of platforms. So the next series of slides going to cover an overview of MIL Standard 461. So the reason I decided to focus on MIL Standard 461 for this presentation is, as far as electromagnetic compatibility is concerned, it's the main standard that actually contains detailed test methods for subassemblies. There is a higher level standard, MIL Standard 464, that I plan to include in one or more of the future webinars in this series. And 464 is a higher level standard that gives the requirements for the platforms themselves. It doesn't contain any specific test procedures, but it gives higher level requirements that require you to go to other standards and follow test procedures. And MIL Standard 461 covers a large number of those requirements in MIL Standard 464. So the scope of MIL Standard 461 is for the control of electromagnetic interference, and as I mentioned, it's for subsystems and systems and subsystems, not full platforms. And I also like to reiterate, not for discrete components. And it's for use by the U.S. Department of Defense. The requirements are laid down specifically, however, the standard allows for tailoring of those requirements. Tailoring of the requirements is usually done by the equipment designer in conjunction with the military procuring department that's buying the equipment. And the tailoring might be done to better match up to the missions that the equipment is going to need to accomplish. The tailoring and testing planned for a particular project is often detailed in a test procedure. And in MIL Standard 461, they refer to electromagnetic interference test procedure as the acronym EMITP. I like to point out that the standard has a main body and an appendix. The appendix reproduces the main body sections and adds additional commentary and rationales on those sections. And it's a very useful and helpful appendix to refer to when there's a gray area or a question in the standard. A lot of times you can find the answer just by checking the corresponding appendix section. The test methods in MIL Standard 461 are named with a five-character name, and the first two characters, the C or R in the first character, represents that it's either a conducted or a radiated test method, and the second character represents that it's either an emissions or susceptibility test method. Section 2 lists applicable documents, basically references to other standards. Section 3 gives definitions of specific terms that are used within the standard. And then Section 4 gives general requirements, meaning that these requirements apply to the remainder of the standard. So they apply to every test method section, and they don't intend to repeat these requirements in each test method section. So I did list I did want to highlight a few of the subsections within Section 4 that as a test lab we use on a regular basis. Section 431 gives the measurement tolerances. So throughout MIL Standard 461, if they tell us, for example, to lay out one of the EUT cables for 2 meters along the front edge of the table, then we have a plus or minus 5% tolerance on that. And if the standard instructs us to measure frequency, we have a plus or minus 2% tolerance on that. So that's an example of the different tolerances that how we just decide what stringency we need to go to there. There's also subsections within Section 4 that detail the requirements for the shielded chamber to be used, the RF absorbers to be placed on the chamber walls, the ground plane within the chamber, and other general requirements such as those. Section 436 talks about power source impedance and mainly talks about the use of a LISN, line impedance stabilization network. The LISN is used on each power line of the main input of the EUT in order to establish a 50 ohm impedance from approximately 10 kilohertz to 10 megahertz. That allows us to take measurements from the LISN measurement port and have an impedance match with our measurement equipment, spectrum analyzer or oscilloscope. And it also establishes a standardized impedance so that testing from one lab to another will have higher repeatability. Here's just a photograph of an example of some LISNs showing their design. They're mainly a shielded enclosure with a single conductor port, although there are dual LISNs that are made. And then in addition, you'll see a RF measurement port as well as a ground stud for grounding them to the chamber ground plane. Section 438 talks about the configuration of the equipment under test during EMC testing, and it also refers to figures 1 through 5. So this figure shows what they call the standard setup for tabletop equipment, and it illustrates a lot of the required cable placement and EUT placement parameters. So the tabletop ground plane itself is required to be bonded to the ground plane with bonding straps that have a 5-to-1 ratio to establish a low impedance connection to ground up through a high frequency. And the external EUT cables are required to be stretched out for a 2-meter length at the front edge of the table to represent a worst-case scenario that they may act as an unwanted antenna. And then you can see that the EUT is placed at one end of the table and the LISNs are placed at the other end of the table. And any equipment outside the chamber that's needed as supporting equipment, the cables pass through an access panel to those pieces of equipment. There's quite a few test methods. This is the table 4 that shows the entire list of test methods contained in the standard. However, for any given project, approximately half or less of the test methods are actually applicable to a given piece of equipment. There's also an applicability table in Section 5.3, which lists the letter A is applicable for certain test methods for certain platforms. And the military procuring agencies also often follow this applicability table when they select which requirements are applicable for a given project. However, there's many military projects that we see as a result of military contracts where it hasn't been clearly defined which test methods should be done. It simply lists MIL Standard 461. In those cases, MET does offer to follow this applicability table and recommend tests, and where a specific list isn't provided. Where there's an L in the applicability table, you have to refer to that specific section of the standard to read the more detailed criteria of whether the test is applicable to a given device or not. And then the S represents that those tests are only applicable where the procuring activity of the military has specifically listed that that test is required on a specific contract. Section 6 of MIL Standard 461 is called Notes, and it basically gives two topics guidance. One is on DIDs, data item description documents. These are separate documents outside of MIL Standard 461 that contain procedures for the overall plan for testing, which they call the interference control procedure, and then it gives the required content for the interference test procedure, which is basically the step-by-step procedure of how testing will be performed. And it also gives the required format for the test report, each separate document for each of those. Section 6 also gives a link to a website, quick search, where you can obtain copies of MIL Standard 461 and other military standards that are approved for public release. And those are free. It's a free website. As long as the military has approved those documents for public release, you can access those there. The next couple slides, I'm just going to give an overview of a little bit more detail of some of the test methods. It's a time-consuming effort and training to get into the details of individual test methods. However, we're considering doing that for at least some of the test methods on some of the future webinars in this series. So for now, there'll be a quick overview. So there's 3 conducted emissions tests in MIL Standard 461, and they cover a range of frequencies as well as types of emissions that are conducted out of the EUT as an unintentional byproduct of its normal operation. So CE101 covers lower frequencies for conducted emissions current measurements, and those measurements are taken with a current probe around each input power conductor in the frequency range of approximately 10 kilohertz up to, in the frequency range of about 30 hertz up to approximately somewhere between 10 and 100 kilohertz. CE102 is the conducted emissions voltage measurement that's taken off of the LISN measurement port in the frequency range 10 kilohertz to 10 megahertz on each conductor. And then CE106 is the antenna, like spurious emissions requirement, and that measurement is taken directly from the antenna port of the EUT. There's several conducted susceptibility tests listed in the standard to cover a range of potential disturbances that would be coupled onto external EUT cables and make their way into the EUT and potentially disturb the EUT. CS101 covers audio frequency susceptibility. CS103, 4, and 5 are various types of antenna port disturbances that would be injected into the antenna port. And then CS109 is for structure currents. So that test has a very limited applicability only to very limited type of devices, but it would represent any noise on the chassis of the EUT as a potential disturbance. And then CS114 is the radio frequency range swept conducted susceptibility. CS115 and 116 are 2 different types of transient disturbances that can couple onto external EUT cables and make their way into the EUT and disturb its operation or cause damage. And the last two conducted susceptibility tests are CS117, which is lightning-induced transient susceptibility, and CS118, which is personnel-borne electrostatic discharge. These two tests were added to MIL Standard 461 version G, and I'm going to talk about them a little bit more in a couple slides. There's 3 radiated emissions tests in MIL Standard 461. RE101 covers magnetic field emissions, which is in the approximately 30 hertz up to somewhere around 100 kilohertz range. RE102 for electric field radiated emissions, which covers a large range from starting between 10 kilohertz and 2 megahertz up to 18 gigahertz. And then RE103 is specific for antenna spurious emissions. And RE103 is an alternate test method for CE106. CE106 is the preferred test method. However, some EUTs have embedded antennas, or they have antennas that contain active circuitry within the antenna itself. And in order to test those designs, RE103 is provided as a test method there. This photo is a piece of equipment we received authorization to discuss. It's made by Hydraulics International, and this was a hydraulic power supply that's used to test the wing rotation pre-flight operation of the V-22 Osprey. And this was an interesting project for us. We needed to exhaust. It's a diesel generator-powered equipment, and we had to operate it during testing, and we had to exhaust out of the chamber and out of the building during testing. And it's fairly large. Some of the test methods that are conducted for MIL Standard 461, the test time is directly proportional to the size of the unit for the test where multiple antenna positions are required. So this photograph gives an example of the antenna and EUT setup within the chamber for RE102 and RS103 testing. There's 3 radiated susceptibility test methods in MIL Standard 461. RS103 covers the magnetic field susceptibility. That test is done with basically a coil antenna at close proximity to the EUT surface, and it covers the frequency range approximately 30 hertz to 100 kilohertz. I'm stating these frequency ranges from memory, and some of them are a little different, but generally just giving you the point that the magnetic field tests usually cover the lower frequency range in the audio range and extending a little above that. RS103 is the radiated susceptibility electric field test, which covers a large frequency range from 2 megahertz up to 18 gigahertz. And it has an optional range of 18 to 40 gigahertz, which is required when it's specified by the military procuring activity for a given project. Usually that test is only going to be specified for devices that include components that actually operate at those extremely high frequencies above 18 gigahertz. One of the things I like to mention to look out for is prior to version G of MIL Standard 461, at the beginning of the standard, the committee included the entire possible frequency range as part of the name of the test, of each test method, even though for each project you don't necessarily end up testing that entire frequency range. I like to point out to watch out for that, because just because a contract might list the name of RS103 as radiated susceptibility electric field 2 megahertz to 40 gigahertz doesn't necessarily mean you need to test up to 40 gigahertz. You have to consider the applicability of that range and ask that question. RS105 is called radiated susceptibility transient electromagnetic field, and this test is often just referred to as the EMP test because the disturbance is supposed to simulate the effect on the ground from a high altitude electromagnetic pulse generated by a nuclear weapon detonated at high altitude above the Earth's atmosphere. So the effect on the ground is estimated at 50,000 volts per meter, and that's the test level of the pulse field. This slide shows a test setup of a RS-105 electromagnetic pulse test that was done outdoors. The test can be done within an EMC chamber if certain clearances are able to be respected from the top of the septum of the radiating lines. But when you have a EUT that goes beyond a certain height, which the EUT needs to be 1/3 the height of the septum, then the test can be conducted outdoors. When you conduct the test outdoors, you have to construct a ground plane. So for this test, there was a ground plane of about 100 feet by 50 feet, ground plane constructed out of wire mesh rolls. And then when you do this test outside, you also have to respect a clearance around the test setup for any other electronic equipment, and then a further clearance for personnel. This test generator is an oil-filled generator which achieves a higher insulation between the pulse generating components inside, so that it enables the design of a 50,000 volt pulse to prevent arcing between components. So the next few slides, I'm going to go over a couple changes that took place between version F and G of MIL Standard 461. One change is that CS106 test method was removed. That test method was developed and added in version F, and it was based on CS06 from version which appeared in earlier versions A through C, and then it was removed in version D. And the committee for MIL Standard 461 concluded that the other test methods, CS115 and 116, already meet the intent behind the reintroduction of CS106. CS106 had a kind of like a double exponential pulse. So it was another transient conducted susceptibility test. CS117, lightning-induced transients, was added to version G. And this was a new test method for 461. However, it's based on RTCA DO160 Section 22, which has been around for quite some time. And it's mostly applicable to safety-critical equipment. It includes DO160 waveforms 1 through 6. It only excludes waveform 5B. And there's different test levels that are included for internal or externally mounted equipment, meaning if the equipment's mounted internal to the platform or external to the platform. And obviously you can see that external equipment would be much more less protected from lightning strikes. And then the application of these waveforms is done through clamped injection. So it's an inductive injection current probe that gets placed around the external cables, the equipment under test, and that couples the disturbance onto the EUT cables and possibly into the EUT. It does not include the direct injection to the pins that's included in RTCA DO160. So this slide shows the calibration setup and the test setup for CS117. An oscilloscope is used as a measurement device, and an open circuit voltage and a closed circuit current are measured on a calibration loop to set the test levels. And then during the test, the injection probe is placed directly around the EUT cables under test, and a current monitoring probe is connected to the oscilloscope and a voltage probe to monitor the injection and the amount of the disturbance that's coupled onto the equipment under test. Another test that was added to version G is CS118, and that's electrostatic discharge, ESD. CS118 is based on IEC 61000-4-2, which is an international standard for performing ESD testing on equipment, electronic equipment. It's been around for a long time. And MetLabs has tested to this test method for the past 30 years or so, because it's been testing to this standard since it's been in existence for commercial equipment. This test is applicable to any military equipment that has a man-machine interface. So as long as a human's going to interact with the equipment and touch it in any way, then it's going to require this test. The test level requires contact discharges up to 8,000 volts and air discharges up to 15,000 volts on surfaces where the contact discharges cannot be applied. That means insulating surfaces, anything that's covered with plastic or a label or something. You would have to use an air discharge method to test for the possibility of arcing through that material to a conductive surface. And the standard requires test system calibration, just like all the other test methods in MIL Standard 461. And there's actually 2 checks performed for ESD. The current waveform is measured into a Pellegrini target, and then the current is measured from the target with an oscilloscope. And the waveform, rise time, different parameters of the waveform. And then also an electrostatic voltmeter is used to measure the voltage charge of the gun prior to testing. So a few other miscellaneous changes to mention in version G is that for freestanding EUT, meaning EUT that would normally be installed on the deck of a platform, it requires now that the tabletop and tabletop ground plane are also used next to the EUT in order to continue to standardize the cable routing and also I guess to control the spacing of the cable off of the ground plane for coupling purposes. For CE102, an additional LISN verification has been implemented. There's a signal that's applied to the LISN and measured with an oscilloscope, and then the same signal is applied to the oscilloscope directly, and then there's a ratio that's measured to verify the LISN impedance hasn't slipped out of specification. Another change that was implemented is for CS114 calibration, whereas previously it was not specific regarding the use of an additional calibration fixture for the injection monitoring probe. Now it is specific to use separate calibration fixtures for those 2 probes. For RE102, there's a couple changes. One, prior to version G, the upper frequency range of measurement of RE102 was determined based on the highest frequency of the EUT. And testing up to 18 gigahertz wasn't required for all EUT. However, that restriction is removed, and now all tests are performed up to 18 gigahertz. The other change is that there's a word, when they describe antenna positions, they changed the word width to area of how you determine the requirement for how many antenna positions. And this change results in clarification and the absolute requirement now to test at multiple antenna heights in addition to the multiple widths that were always accounted for whenever an EUT is taller than the single beam width of an antenna at any given frequency. So each measurement antenna that's used has a beam width characteristic that's established, that's shown by the manufacturer, and it can only illuminate a certain width of EUT in a given position, and then the test has to be repeated with the test antennas in multiple positions for larger EUTs. And obviously this affects test time. And a similar requirement, same exact change in requirement is for rated susceptibility, RS-103. So there may be more antenna positions required for the same EUT as compared to if that EUT was tested the previous versions. Now, I'd like to talk a little bit about planning for MIL Standard 461 testing. So for those who are in the position of designing or supporting testing of their company's designs, it's definitely, there's some planning that should be done. A good test lab can, be as prepared as possible, but there's a lot of aspects that require the manufacturer's cooperation and involvement in order to have the highest level of quality of a test program take place. So EMC is difficult to design for, meaning it's difficult to design to pass and have a high level of confidence of passing tests simply based on design concepts. So there are best engineering practices that can be followed. However, there's a high failure rate for several of the MIL Standard 461 tests in almost every project that comes through. It's stringent testing, and the best thing that can be looked out for during the design process is optimizing the shielding and the filtering. And these are aspects that I plan to elaborate on in future webinars in the series, because they can consume a lot of time and details just by themselves to elaborate on those items. However, if you are able to, the design and the budget affords a shielded enclosure, Faraday cage type design enclosure, then that's, in most cases, it's required. If there's any electronic components in the device, you're going to need a Faraday cage design to enclose those in order to pass these requirements. And in a lot of cases, filtering will be required on the power input and also on the signal input lines in order to meet these testing requirements. Another key is to plan right from the start to perform pre-testing, not just allow time and budget for final testing, however, to perform pre-testing. And the level of pre-testing can vary. It's not, I wouldn't say it's absolutely required to perform full testing of every method as pre-testing, although it's not a bad idea. However, we often recommend certain test methods that have the highest that we see the highest rate of failure. We recommend those test methods be performed as pre-testing, and then in order to save time, but still save time and cost, but still create the potential for failure if it's there, we have some parameters of the test that we can speed up or we can deviate from the standard. But based on MetLab's experience, we can still say that they're going to represent a strong potential for failure if there is one. And that level of pre-testing has proven to be very effective. It allows for design changes to be anticipated at that point ahead of time, and then the design tweaked before final testing is conducted. So it allows for a greater success on final testing. During planning for testing, you want to consider certain specific details about the equipment under test. You want to think about how will you configure your equipment actually during EMC testing. A lot of times, the setup that the way the equipment is going to be configured in the installation isn't going to work exactly for EMC testing. Also, MIL Standard 461 doesn't allow necessarily for the actual installation conditions. They do want you to simulate actual installation conditions. However, they want you to also follow certain rules that are laid out in the standard. So input leads need to be exactly between 2 and 2.5 meters. So you're often shortening input leads before we start testing. And then all other external cables, if those cables would be greater than 10 meters in the installation, then at least 10 meters are required to be included for during testing. And if those cables will be less than 10 meters in the actual installation, then you need to work together with your test lab to make sure that you provide cables that are at least long enough to accommodate the setup in the lab. So those cables, if they need to exit the chamber and connect the supporting equipment, you're going to need to know the size of the chamber and how far away will the supporting equipment be. Or if those cables are just going to connect to another port on the EUT itself, they need to at least be long enough to come up to the front of the edge of the table and run for a straight 2-meter length, and then have the additional length to loop back and come back to the EUT. You need to think about what will you need supporting equipment. So during EMC testing, you need to establish a mode of operation. You should attempt to simulate all functionality of the EUT within one mode of operation, because that will allow you to run the tests one time each. However, if you have a complex device that can do a lot of separate different functions, but it can't do them at the same time, then you may need to repeat each test more than one time. And that's something you want to establish from early on in the design process, because it's going to drastically increase your budget for testing, both in time and cost, if you have to run test methods more than one time. You want to make sure your mode of operation is a worst case mode of operation from an electromagnetic point of view. So for example, if your equipment can operate at different output levels, often the highest output level creates the highest electromagnetic emissions, and often the weakest or lowest output level may be the most susceptible to disturbances. So you may, in that case, establish a different mode of operation for emissions tests and a different mode of operation for susceptibility tests. And then the other aspect of EUT modes of operation for EMC testing should be continuous operation for long durations. If your EUT in its mission only you push the button and it operates for 30 milliseconds and it stops, it's not going to accommodate EMC testing. So you may have to come up with a special test script or even a test firmware that causes the EUT to operate continuously during EMC testing. You also need to consider a monitoring method and be prepared to provide that monitoring method to the test engineers. The monitoring method should provide a visible indication that the EUT is operating properly. That could be a laptop computer, support equipment with a test script that displays past results when it's working properly. And the monitoring method should provide automated real-time results. So it's better for a test operator or even for a test designer that's witnessing testing to be able to simply observe the output and not have to interact with the equipment continually in order to update test results. And the supporting equipment needs to be isolated from the EUT. So typically supporting equipment is outside the chamber, the EUT is inside the chamber, and during tests like RE102 and RS103, there needs to be isolation. So during emissions tests, ambient emissions can enter the chamber riding in on the EUT cables that pass from the EUT to supporting equipment. And during susceptibility tests, the disturbances that we generate with our test equipment can ride on the cables and out to the supporting equipment and directly affect the supporting equipment and give a false indication of failure. So any shielded cables that are used should be grounded at the chamber bulkhead. And if at all possible, all shielded cables should be used to enable for that type of isolation. And then also consideration should be given to use an antechamber to contain the supporting equipment that's located outside the chamber. And the antechamber can be connected to the main chamber with a shielded pass-through so that there's no exposure to ambient emissions. So just in conclusion, I wanted to just include some of MET's related capabilities and see if there's any questions. Okay, before I get into that, we did have a question that's submitted. So the question is, for CS118 ESD for 461G, is there an alternate method for the voltage calibration that does not use an electrostatic voltmeter? Example, using a scope with some sort of voltage divider. So there's no method provided by the standard that I've seen. There may be a method that exists in the industry that I'm not aware of. However, the electrostatic voltmeter, for me, is actually a device that's newer to me in my history. I've been doing EMC testing for about 16 years, and it's only been within the past year when we geared up for 461G that I became familiar with the electrostatic voltmeter, exactly how it's used for this. So it's a small battery-operated device, and what it does is it actually, when you put the ESD generator in air discharge mode, and you pull the trigger and you charge the gun, the tip of the generator, this voltmeter actually measures the difference of potential between the tip and the electrostatic voltmeter. You actually don't discharge the gun during the test. It stays energized, and the potential, voltage potential is measured. So an oscilloscope requires a current or requires a voltage in a conducted way to be applied to the input. So you would have to have some type of transducer that would transduce from a difference of potential and then generate an equivalent voltage or something of the sort. And I haven't seen a device like that, although I think it would be possible. And maybe there's a test equipment. Maybe a test equipment manufacturer has designed that type of transducer for an oscilloscope attachment, but I haven't seen that before. So, as I said, I historically haven't been familiar with electrostatic voltmeters. Someone else here at MET found the electrostatic voltmeter that we ended up purchasing, and I don't remember what it is off the top of my head, but I'd be happy to share that if anybody wanted to follow up on this question, with an email for me. And I don't remember if my email address is attached here, but there is an email address on this presentation, info@metlabs.com, and we could get the information that way. Thanks for the question. Okay, so just wanted to go through. There's a couple slides on the related capabilities. So just to highlight, MET does have full capability for 461 for all the versions and all the test levels that are included. And we have already been equipped and experienced to handle the new methods CS117 and CS118 because we've already tested to the standards that those tests were adopted from for years. We also test to RTCA DO160, which is for commercial aircraft equipment, and it has a lot of similarities in the test methods to MIL standard 461. We also do testing to IEEE 299 for shielding effectiveness, and several power quality standards, MIL standard 704, 1275, and 1399. We have a 45 kVA programmable power supply with filtering capability to fully handle that power capability within our chambers. And out in our Santa Clara lab, we have a reverb chamber that can test up to 20,000 volts per meter for radiated susceptibility. There's some requirements like that included in MIL standard 464 as well as DO160. And we can test the DO160 section 22 for all the waveforms and CS117 for all the waveforms. And as I mentioned, we have the RS105 high altitude electromagnetic pulse capability up to 50,000 volts per meter. I think our generator can actually go higher than 50,000 volts per meter, but that's the requirement of MIL standard 461. So that's about all, and if anyone had any additional questions, I'll hang on for a minute and we can answer those. And as we mentioned a few times, we do plan to conduct a series of webinars that will follow on to this webinar, and I do have a lot of ideas of popular and helpful topics that we'll include, but I just wanted to also mention I'd be highly open to any feedback, any requests for specific content for any of the upcoming webinars. I'll be happy to work those in. Those presentations aren't all prepared yet, and we'll be tailoring those to the best group of content that we decide based on everybody's feedback.